So you want to do regression with your artificial neural network, and you have sum squared error as your error function, and you have linear functions at the final layer of your neural network. If you wonder how backpropagation transfers all of those gradients through the sum squared error and the linear functions at the final layer of your neural network, do not miss this video. Stay with me. Right, so let's say we've got this simple neural network, right? So we have one input layer here. It is d-dimensional, right? So this is my input layer. It has d dimensions. You've got loads of weights that are connecting this input layer to the output layer. And finally, you've got h number of output layers, neurons in the output layer. And you have weights on these edges, so your typical neural network. And these Z guys over here, they're called the pre-activations, right, of your final layer. So let's say this is the regression task. In a regression task, as you know, the typical function that you use at the final layer of your neural network is linear function. So if you want to compute the predictions of your neural network after the final layer, so the first dimension of your prediction in the task of regression, y hat 1, is a linear function of the pre-activation to that particular neuron. So y hat equals the linear function of the pre-activation z1. Same story, y hat 2, the linear function of L2, right? So the whole reason for that is that this the function here is a linear function in each one of these neurons. Right? Because remember, in regression, you want to predict real valued numbers, right? The price of oil next week, the price of the stocks next week, the amount of gasoline that this car is going to burn in the next 2 hours, this sort of thing, right? They're all real numbers. And finally, you've got these predictions, right? Y hat 1, y hat 2, y hat h. Now, one thing I need to make sure you're aware of is that because this is a linear function, y hat 1 is actually equal to z1. Y hat 2 is actually equal to z2, right? Because it's a linear function, it doesn't change the pre-activations. And now, let's say you want to, compute the error function of compute the error of these predictions. So you need to look at the ground truth, right? So let's say you have a ground truth vector here that has h dimensions, y1, y2, yh. So using the sum squared error, you will compute the difference, the gap between your linear outputs and the ground truth, right? Now, so the first dimension of your error vector is going to be E1. So the squared error definition is 1 over 2. The ground truth minus the prediction, power 2, right? Raise it to the power 2. So that is E1, the first dimension. The second dimension, the same story, only with Y2 and Y hat 2 all the way to EH. So this is your error vector, right? So one input vector comes in, it has d dimensions. You have h number of a vector of predictions that has h values in it. You have a vector of ground truth that again has h values in it. So you compare these two predictions and ground truth vectors together, and it results in a vector of errors that has h elements again. And each element is computed using the squared error function, right? So why do we call it sum squared function? Is because you sum all of these elements together, and that scalar that results out of all of this madness is the error corresponding to that one input vector of d dimensions that was put into your neural network. Right? Let me just go over 2 rules that you need to get comfortable with if you want to, fly through this video. Number 1 is, in calculus, the derivative of a sum is the sum of the derivatives. Now, what do I mean by that? Let's say you have a summation, right? Let's say you've got f of x plus g of x, right? And you want to compute the derivative of this this combination, this sum, with respect to x. Now, this is the derivative of a sum, right? So the rule says it is equal to the sum of the derivatives. So individual derivatives, right? So that's rule number 1. Rule number 2 is the chain rule. Now, the particular part of chain rule that I'm interested in here is that, let's say you have a function of x to the power something, k. Now you want to take the derivative of this entire thing with respect to x. The rule says k comes down times f of x to the power k minus 1 times the derivative of f of x with respect to x. And if I want to just go on a tangent here and just to tell you why that's happening, because according to the chain rule, you can only take direct derivatives of functions with respect to derivative to the variables that they're a direct function of. What do I mean by that? Is that, let's say you have f of x to the power 2, right? The entire thing to the power 2. And you want to take the derivative of that with respect to x. Now, f of x squared is not a direct function of x, but it is a direct function of f of x because of f of x squared, right? So it's, if you want to compute this, it's as if you were doing this, f of x squared, the derivative of that with respect to f of x, and then times the derivative of f of x. Now that is a direct function of x. Now you can do that. Now, you notice that this chunk is equal to this chunk. So what about this chunk? Now, if I want to compute this guy, it's very simple, isn't it? It's the rule of power. So 2 comes down, you repeat f of x, 2 minus 1, the power, 2 minus 1. You see, this is the same as this, except k is equal to 2. We want to compute the partial derivative of the error with respect to the pre-activations. Remember these pre-activations, these z1, z2, one of them, z1, z2, zh, whichever, right? I want to show you how you can derive that. So I want to go from the error all the way to the pre-activation and transfer those gradients, right? So let's get started. So as I said, the sum squared error says the error equals the sum of all individual errors in one input, in one error vector. Remember, that error vector corresponds to one input data that happens to have d dimensions, right? So we are here talking about this e is a scalar, a error value corresponding to one input data that was put into your neural network. Remember that, okay? Let me put it this way. So we've got the sigma, and we know that e sub I is, each one of them is equal to e1 over 2, the ground truth I minus y hat I squared, right? And I goes from 1 to h, right? And you immediately notice that this 2 over here, this 1 over 2 can actually go to the very beginning, they get out of the sigma. That's just a constant. And we want to take the derivative of this entire thing with respect to zk. Now, what is k? K can be 1, 2, all the way to h, right? Because you have h number of pre-activations, right? So let's write it down. So the partial derivative of this entire thing, 1 over 2 sigma, which is the sum of this difference with respect to zk. Right. Now, again, you notice that this 1 over 2 is a constant, so it survives the derivative, right? The derivative operation, so it can just get out of it. Right? So imagine this 1 over 2 outside, and then you notice something very interesting that we have just talked about, literally. So let's say 1 over 2 comes out, and we've got, again, the same story. The derivative of a sum, I'm hinting something here, right? A sum with respect to zk. So remember, rule number 1, the derivative of a sum is a sum of the derivatives. The same story here. We have a derivative of a sum. So this equals, let's just keep 1 over 2 the same, the sum of the derivatives. So literally the sigma comes out, right? And then you've got the derivatives. The derivative of I minus y hat squared with respect to zk. Right? Again, remember, I goes from 1 to h. Right. Now, how do we compute this? First and foremost, you do notice that yi minus y hat I squared is not a direct function of zk. So here we're gonna employ the second rule, the chain rule that I just talked about here, right? The chain rule. So something to the power to power k with respect to a variable, right? So how do we do this? So according to the rule, so 1 over 2 survives, right? We've got the sigma. The sigma doesn't go anywhere. Let me put a bracket here just to make it neat. So we've got 2 comes down, right? Or maybe let me make it simpler. Let me make it simpler. So yi minus y hat I squared is not a direct function of zk, is it? It's not, right? So first you need, using the chain rule, you take the partial derivative of this guy with respect to y hat, because it is a direct function of the outputs of your function, right? And then the outputs of your network, those guys are a direct function of the pre-activations, aren't they? I mean, just as a reminder, there you go. So each one of these y's are a direct function of the pre-activation, and it's a linear function, happens to be a linear function, right? So there it is. Now, so this bit was chain rule, right? This guy, this chunk over here is not a direct function of zk. It is a function of y hat I, but then you've got and then y hat I is a direct function of your pre-activations, right? So that's how you break them into 2 pieces. Let's focus on this guy. This looks a little bit tricky, right? This chunk over here. Okay? Again, using chain rule, we have something to the power 2. We want to take the derivative of that with respect to a variable. How does that work? According to the chain rule that I told you about, so 1 over 2 stays. We have the sigma, right? The power comes down times the base remains only, well, the power decrements, right? So 2 minus 1 is 1, so I'm not going to even write it, right? Times, now, the derivative of the base with respect to your y hat, right? This is what it is. This is exactly what we talked about, the chain rule, right? So here f of x is, what is f of x in this example? F of x is yi minus y hat I. What is k? K is 2. What is x? X is y hat I. Right? Just pause for a sec, let that sink, okay? If it's too much. Give yourself time. There's no rush. Now, moving on. So this whole thing was derived, and let me change color. Times, now this guy comes down, right? So I haven't touched it yet. Y hat I zk. right? So right off the bat, this 2 comes out and gets cancelled out with 1 over 2. So we're already simplifying things. So that's good. Now, this guy over here, can we break it down into 2 pieces? Just because I just don't feel really comfortable with it. And you notice that we have this rule here, right? So the derivative of a sum is the sum of the derivative. And guess what? The derivative of a subtraction is also the subtraction of the derivatives. Doesn't make any difference. So by the same logic, you can break this down into 2 pieces. Break this guy down into 2 pieces. How? So it is equal to the sum of, so you have yi minus y hat I, so the first term remains intact, times, now this guy breaks, the subtraction of the derivatives, yi with respect to y hat I minus y hat I with respect to the derivative of that with respect to y hat I, right? Times the last term survives as it is. Now, good news. So the derivative of the ground truth with respect to the outputs of your network, they are independent of each other, right? So the labels of your dataset have nothing to do with the predictions of your network. So that guy is 0. What about this guy? The derivative of something with respect to itself is 1, right? So this guy is 1. So 0 minus 1 here, so we got 0 minus 1 is minus 1, right? So this whole thing becomes minus 1 between the 2 brackets. And minus 1 could just get out of the derivative, right? Sorry, they get out of the summation, the sigma, right? So let me just go to the next slide. So we have minus 1. That minus 1, I'm just going to keep it outside the sigma. We got this over here. And now here, the first term remains, right? So you have yi minus y hat I. The second term was minus 1, that we've already taken care of. The last term, y sub I, the derivative of that with respect to a particular pre-activation. Y hat I with respect to a particular activation. Now, let me tell you a story about this guy. 2 things can happen. Either I is equal to k, or I is not equal to k. Meaning that you are either taking the derivative of a y with respect to its corresponding pre-activation or with respect to some independent activation, pre-activation. So you're either computing the partial derivative of y sub I1 with respect to z1, so I and k are equal, in this case 1 and 1, or you're taking the derivative of y sub I1 with respect to z2, z3, zh, whatever. In that case, y sub I hat and z2 are independent, so that derivative is going to be 0. But what about the derivative of y sub I hat with respect to z1? Remember, z1 and y hat of I, they're equal. Remember, I said in the very beginning, this is a linear function, right? So y hat I 1, y hat 1 is already equal to z1. So derivative of y hat 1 with respect to z1 is going to be what? It's like the derivative of z1 with respect to z1. The derivative of something with respect to itself is going to be 1, right? So what is the derivative of y hat 1 with respect to z2? It's going to be 0. So by the same logic, if I and k are equal, this term over here is going to be 1. And if they're not equal, they're independent, the derivative is going to be 0. And remember, of all of the i's that we are counting here, I goes from 1 to h. If I and k are not equal, this guy becomes 0, and this multiplication will become 0, And so that term just gets cancelled out in the sigma. So the only combination that matters, that's going to survive throughout this madness, is only when I and k are equal, right? So in other words, this sigma can get simplified. So you don't need a sigma anymore, because any other term in the sigma will get zeroed out, effectively. So this derivative is equal to minus y, remember I'm writing this guy, and this is the case where I and k are equal, right? So this becomes yk minus y hat k times, and when I and j are equal, this guy is 1, right? So times 1, and I don't need to even write it. So in other words, this becomes y hat k minus yk. Now, what do I mean by this? As a simple example, if I were to take the partial derivative of the entire error, this whole summation, with respect to z2, what does that mean? It means the whole madness that we went through simply means this, right? It simply means the derivative of error with respect to a given pre-activation, let's call it z2. It's simply this, y hat 2 minus y2. So the second prediction of your prediction vector, the second element of your prediction vector minus its corresponding ground truth is gonna be equal to the partial derivative of your error function with respect to that particular pre-activation z2. That's all that it is. Now, just for your own sake to pause and ponder, if you feel if you need to, here it is. This is the whole story, everything that I talked about with the rules that I've used. So you can just pause here and then just go through the entire thing. Very simple, very neat and very simple. Trust me. And this is the final conclusion, right? Depending on the value of the comparison of I and k, this becomes the final output of the partial derivative, right? I hope that this has been informative for you. If you have any questions, feel free to post them in the comment section down below. And if you like the video, make sure you like, subscribe, and guess what? Share the video so more people can learn from this. And if you're interested, you can follow me on Twitter, LinkedIn, Facebook, and Instagram. The links are in the description to this video. Until the next time, take care of yourself. Bye.